Hi everyone, we're going to continue on with our acid and bases. So in our last video we talked about how we could calculate Ka from pH. So last we used, you were given pH and I needed to find Ka. Of course we could do the opposite of that, so we could calculate pH if we were given Ka, which we'll do in just a minute. But there's another piece of information that we can find or calculate when we're talking about concentrations, and specifically we call this percent ionization. So how much of the acid did we really get to ionize or dissociate in water? So percent ionization is going to be the concentration of hydronium at equilibrium. So I designate that here by saying it has to be at equilibrium with the subscript EQ. And then I'm going to take that concentration and divide it by the concentration initially of the acid that we have. So concentration of my hydrogen ion at equilibrium over then that concentration initially of the acid that we're starting off with. And since it's a percent, we'll multiply it by 100. So in the last video, we used formic acid, and we specifically looked at how formic acid was dissociating. And we found, or we calculated, that the hydronium concentration is 4.2 times 10 to the negative third molar. And we know that initially we started off with 0.1 molar of formic acid. So to find percent ionization, I'm going to take my hydronium concentration at equilibrium, which was this, divided by the initial concentration of formic acid, which was 0.1, multiplied by 100, and I get 4.2%, which should also make sense because at equilibrium, if we can maybe go back, if we remember at equilibrium, formic acid was 0.0958 molar. We lost very, very little of this. So that means HCOOH really didn't dissociate into ions hardly at all. So it should make sense to us that our percentage for percent ionization is very low, and it is. Okay, so again, from the last example, we calculated Ka from pH. But now what happens if we want to do the flip of this? We want to do the reverse. So actually I want to go back, just kidding. Let's talk about just for a second what Ka means, or kind of review. So Ka, we know, is just the acid dissociation equilibrium constant, and specifically we use that for weak acids. So I want us to know or refer to Ka as indicating, it indicates the strength of a weak acid. So it indicates the strength of a weak acid. So percent ionization is just another way that we can show strength in terms of a weak acid. So here we see that it ionized only 4.2%. Ka is another way that we can indicate strength of a weak acid. The stronger the acid, if we're talking about percent ionization, then that means that my percentage is going to be higher, because that just means I have dissociated my acid, that weak acid, into more ions. So if that's true, then the percent ionization should also then be greater. Okay, so let's go back to this one. So let's calculate pH from Ka. Based on this, we have 0.3 molar solution of acetic acid, and that's at 25 degrees Celsius. They've given us a reaction here, so I don't have to write one on my own. They're also telling me that Ka for acetic acid is 1.8 times 10 to the negative fifth. So first step I told you is I want you to write a reaction. Well, that's already given to you. So then the second step means I want to write an equilibrium expression. So if I'm writing the equilibrium expression, Ka, that should equal product of the products, so H3O plus times the concentration of C2H3O2 minus over, since water is a liquid, I'm not going to use it in my equilibrium expression, so I'm just wanting to do the concentration of acetic acid. Okay, so first things first, I want a reaction. Since they already gave it to you, let's do an equilibrium expression. They also then gave us Ka. So our goal is to find pH. Equilibrium expression is here. It matched up with what we had. The next step, let's draw an icebox. So initially, we started off, they told us 0.3 molar of acetic acid. And I know that I have 0 then of my products initially. So if I'm thinking about my change, I know that the change is just going to be as simple as I'm going to be losing my acetic acid, and I'm going to be gaining these ions. And if I think back to acetic acid, it's H, C2, H3, O2. So if I'm taking away this H+, that means I'm going to be left with 1 acetate ion, which is a minus. So I have a 1-to-1 ratio of ions, which is why I can say this is plus X and plus X. Not 2X or 3X or anything like that. So just plus X and minus X here. Okay, let's look at then what we would have at equilibrium. So at equilibrium, we could say that this would be for acetic acid, 0.30 minus X. This is just going to be plus X, and this is just going to be X as well. Well, I know, according to my equilibrium expression, I know this. And I know that Ka is equal to, I know Ka is equal to 1.8 times 10 to the negative fifth. And right now I just have these pieces. I just have X and X over 0.30 minus X. Well, it doesn't help me much because I don't know what X is. So because these are weak acids, and because typically X is such a small number, we have a rule that we have kind of come up for ourselves in chemistry. It's called the 5% rule. And pretty much we just assume that X is going to be so small that if I'm taking at equilibrium acetic acid's initial concentration, which was 0.3, and I subtract X, I'm probably still just going to be left with 0.3 because X is going to be so small that it's really not going to affect this number really at all. So on these ice boxes, I want us to assume that X is super small. And I'm calling this the 5% rule because at the end, if I take 5% of what we have found for X, then, and I see that it's less than 5%, then we were fine by assuming or ignoring that X was going to be bigger than maybe what we thought that it would be. So for right now, just follow along with me, we're just going to assume that X is going to be super small, that it's not even going to make a difference here. So if I assume that, then really this just becomes 0.30, and this becomes X, and this becomes X. So I could plug in back to my equilibrium expression. I have X, and then instead of 0.3 minus X, let's just say that now it's just 0.3. Well, now this makes it a lot easier to solve. So if I solve for this, then ultimately, I think we have this actually on a couple other slides, so let's just go there. Okay, so I have 0.18 times 10 to the negative fifth, that's my Ka, equals X squared over just 0.3, because now we're just assuming that this X is small enough that I don't even have to worry about it. I can ignore it, it's negligible. So if I multiply both sides by 0.3 to get this out of the denominator, I'm going to get 5.4 times 10 to the negative 6, and that equals X squared. But I want to know just what X is. So if I square root both sides, I get X to equal this. Now, if X equals this, ultimately, I know if I go back to my ice box, my goal was to figure out what's the pH for this hydronium concentration. How much hydrogen ion did we have at equilibrium? Well, I know now that X, we just calculated that X is equal to 2.3 times 10 to the negative third molar. So if I want to find pH, I want to do the negative log of that, which is here. So I'm going to take the negative log of 2.3 times 10 to the negative third, and I get a pH of 2.64. And remember that all pH scales should always have 2 decimal places. So So always make sure you have 2 decimal places, regardless of significant figures or not. We always want pHs to have, or POH, to have 2 decimal places. Okay, on this next problem here, it says calculate the pH of a 0.2 molar solution of HCN. It says refer to table 16.2 or appendix D for the value of Ka. Well, the Ka for this is 4.9 times 10 to the negative 10th. So the Ka for HCN is equal to this. So you're going to calculate pH of a 0.2 molar solution if you're given Ka. So I would like you to try this, please, for homework. We'll look at it first thing tomorrow when you come in. Okay, we just have more percent ionization here. So it says calculate the percentage of HF molecules ionized in a 0.10 molar hydrofluoric acid solution. Let's assume for this one, if I looked up my Ka value, let's say that Ka is going to be 6.8 times 10 to the negative 4th. So this problem I want you to do for homework, and this problem I want you to try. Okay, let's talk then quickly about Le Chatelier's principle. Okay, so ultimately, let's just say that we have, here we have acetic acid, and we know that acetic acid is going to go from HC2, H3O2, and then when it reacts with water, it's going to break down or try to ionize as much as it can into hydronium ion and acetate ions. Okay, so I'm left with those 2 things. So if I'm looking at my graph here, this shows that as the concentration of a weak acid increases, so as my concentration for a weak acid increases, that's on my x-axis. So I have 0.05, 0.1, 0.15. So I'm increasing in acid concentration. But what's happening to the percent ionized? I see that percent ionization will decrease as the acid concentration increases. And ultimately, this is going to be consistent with Le Chatelier's principle. So if percent dissociation remained constant, as the acid concentration increases, then the concentration of all 3 are going to have to increase at the same rate. So if my percent composition stays the same, if it stays constant, or my percent dissociation, percent ionization, if it remains constant, then that means if I increase the acid concentration, then that means that my 2 ions that I'm producing, so if I'm increasing this concentration, ultimately the concentration of these 2 will also go up if my percent ionization stays constant as well. So because though I have 2 products, I'm having 2 ions here, and I really only have 1 reactant, because remember, we're not including water in our equilibrium expression. The total concentration of the products is going to increase faster than the concentration of the reactants. So because of this, we have to offset the acid concentration by decreasing the percent ionization or the percent dissociation. So because I have more product that I'm producing than I have reactant, because remember, water is not a part of our equilibrium expression. So because I have more of this and less of this, I have to, I know that my product concentrations are going to increase faster than my reactant concentrations. I have to offset this by, if I have more acid concentration, or if I increase the concentration of acid, the dissociation percentage or percent ionization is going to have to decrease to allow equilibrium to continue to move back and forth. So to allow Le Chatelier's principle to move back and forth. Okay, we have polyprotic acids. We just know that polyprotic means that it has more than one acidic proton, meaning also acidic proton, I don't like that. Let's call it an ionizable hydrogen. I like that better. And remember that an ionizable hydrogen is just a hydrogen that is easily removed from an acid, thus making hydronium concentration in water, or increasing hydronium concentration in water. So H2SO3, that's a polyprotic acid. Is it a strong acid? No, it's a weak acid. But ultimately what will happen if I have a polyprotic acid, we're going to take a hydrogen off at a time, one hydrogen off at a time. So H2SO3 is going to take a hydrogen off, so it's going to donate a hydrogen ion. I have H plus here, and then I'm going to be left with HSO3 minus. Well, now this also becomes it's part of that polyprotic acid. It's still an acid. It has a hydrogen that it can donate, so this is still an ionizable hydrogen. So SO3 can get rid of this hydrogen, giving me H plus, and then the sulfite ion. So I can see here that we have a Ka1 and a Ka2. The difference between the Ka for the first dissociation and the subsequent Ka values, you're going to see that my Kas are going to decrease dramatically as I continue to take off a hydrogen. It's easier to remove the first proton, the first hydrogen, from a polyprotic acid than it is to remove a second hydrogen. So Ka values just become much smaller as we keep removing successive hydrogens. So it makes sense that this one is going to be a lot larger than the Ka2 because it has to happen in steps. So we talked about weak acids. We can also talk about weak bases. We know that weak bases, if they react with water, they are going to abstract a proton from water. So if I have a weak base and I'm reacting it with water, water here is now going to act as the acid. Let's say that we have ammonia here as the base. So I'm going to end up making NH4 plus and OH minus. So I have my acid-base conjugate pairs here. If I write an equilibrium constant expression, just in general, for a general reaction for a base, let's say that we have our reaction, we have a base plus water, and let's say that'll be liquid form. Weak base, so I want to use double arrows because it's only going to dissociate partially. I'm going to get HB plus because the base is going to accept a hydrogen, and then I'm also going to produce hydroxide ion, OH, and that'll be minus. And both of these are aqueous because they're ions now dissolved in water. So if I write the equilibrium expression for this reaction, I have HB, and that should be a plus, guys, sorry. I have HB times the concentration of OH minus. Oh, just kidding. Apparently we made this B minus. Okay, let's go back. So this B minus for my base plus H2O is going to make HB plus OH minus. So I have concentration of HB times the concentration of hydroxide over then the concentration of the base that's the reactant, and I don't include water because it's a liquid. So instead of writing Ka for an acid, like we write Ka for acid dissociation, we're going to write Kb here to represent weak base dissociation. So Kb can be used, the base dissociation constant, can be used to find hydroxide concentration. And we can also think of, if we know hydroxide concentration, we could find hydronium concentration or hydrogen ion concentration, and if we can find that, then we can find pH. Or we could also find hydroxide concentration, find POH, and then ultimately find pH. So these are some common weak bases. This is table 16.4 in your book. Ultimately, if you look kind of closely at this, I know it's probably really hard to see on here, but there's a lone pair here, lone pair here, lone pair, lots of lone pairs, and even more lone pairs. Usually weak bases contain one or more lone pair, and it's just because it's necessary for that lone pair to bond then with a hydrogen ion. So most weak bases should contain a lone pair, and a lot of them actually contain nitrogen. If they contain a nitrogen that has a lone pair, a lot of weak bases classify under a group that we call amines. Okay, so just like we did with acidic solutions for pH, we could also find pH for a basic solution. So this says, what is the pH of a 0.15 molar solution of ammonia, NH3? So the first step, I would say, write your reaction, write your equilibrium expression. Those are the first two steps, and they're done here for you. So I have NH3 reacting with water, making ammonium ion and hydroxide ion. So then my equilibrium expression looks good. I have the product of the products over the reactant, and I also gave you KB, because we're on bases. So I gave you the base dissociation constant, which is 1.8 times 10 to the negative fifth. So my goal is to find pH. That means I want, ultimately I want to know the concentration of H3O plus. Well, I know that H3O plus and OH minus are related because I know that the hydrogen ion concentration times the hydroxide ion concentration equals 1 times 10 to the negative 14th. That's the ion product constant for water. So if I know this, and I know this is always true, I could find this, and then that means I could find pH. So there's our steps, or there's our goal of what we want to do. So we should make an ice chart because I'm dealing with some concentrations and I need to figure out some things. Ultimately, I know that initially I'm starting off with 0.15 molar of NH3. They gave us that here in the problem. So I'm starting off with that. That means I have 0 molar of my products, of my ions. And then I know that ultimately this is just going to change by minus x plus x plus x. So at equilibrium, I should say 0.15 minus x plus x plus x. Should you still show your change? Yes, you should. This isn't technically an icebox, but we should still show the change. So if I do something similar to what we did in the last one to find pH, I can just assume that x is going to be so small that it's really negligible here. So I could still say, like we had for our KB, that was NH4 times the hydroxide concentration over ammonia. So if I plug in what I have here, instead of saying this is 0.15 minus x, let's just call it 0.15 now. Because again, we're assuming that it's so small that it's not even going to make a difference if I subtract x from this. So in H4 we have x times x over 0.15. And we knew that KB was equal to 1.8 times 10 to the negative fifth. So I could say 1.8 times 10 to the negative fifth equals x squared over 0.15. Let's multiply both sides by 0.15, so we're just doing some algebra now. I get 2.7 times 10 to the negative 6 equals x squared. If I square root both sides, this is what I get, 1.6 times 10 to the negative third for my x. So that means that the hydroxide concentration, OH minus, equals 1.6 times 10 to the negative third molar. But they asked me for pH. So there's a couple different ways we could do this. I could take, if I have OH concentration, if I have hydroxide concentration, I could take the negative log of this, and then I could take 14 minus what I get here to get the pH. Or I could take 1 times 10 to the negative 14th and divide it by this to get the hydrogen ion concentration, and then I could take the negative log of that to find pH. So either way that you do that, you would be fine. So here I knew OH concentration was this. I took the negative log of that concentration to give me pOH. So the pOH here is 2.80. I know that pH plus pOH equals 14. So if I know pOH is 2.80, I knew that that's equal to 14. I can find pH, and that's 11.20. And since pH is greater than 7 here, we know that it's a basic solution, which should make sense then because we're talking about a weak base dissociation. So it's the same steps, the same stuff that we were doing with acid dissociation constants. It's just that now we're talking about them also with weak bases. So ultimately there are two types of weak bases. There are neutral substances, that have lone pairs, or those non-bonding pair of electrons. The non-bonding pair of electrons are important for a base just in the terms that it's that pair of electrons that are going to accept a proton. So like we just said on that last table, most of them have nitrogen on them, or in them, and then if it has a nitrogen, we usually classify that somehow as an amine. Another type of weak base is an anion of a weak acid, specifically if we have a ClO minus. That's another type of weak base. Okay, so Ka and Kb should be related somehow, and they are related in the fact that if I take the Ka and I multiply it by the base dissociation constant, I'm going to get the ion product of water. So Ka times Kb should give me Kw. So let's do an example of this. I think we don't really have enough room, so let's make a new page. Okay, let's say, for example, that we were given NH4 plus H2O, and that's going to break down, NH4 plus H2O is going to break down into NH3 and hydronium. But then let's say that we could also have NH3 reacting with water. And when NH3 reacts with water, we can get ammonium ion and hydroxide ion. Okay, so if I'm looking at these, NH4 plus, if I'm looking at this first one, is going to act like an acid. So here's my acid. And I know that because it's donating a hydrogen to become NH3. So here's the conjugate base. And that means that water here has to be acting like a base. So then hydronium has to be the conjugate acid because it was accepting a hydrogen. NH3 here is going to be my base. That means water has to be the acid. So if NH3 is the base, then that means that NH4, will you close the door, sweetheart? That means that NH4 has to be my conjugate acid, and OH minus has to be my conjugate base. So I just want to write the equilibrium expression for the first one, and that's going to be NH3 times H3O plus over NH4. And since specifically we're talking about, and that's NH4, sorry, plus. So specifically, that's when we're thinking about ammonium group acting as an acid. So I'm going to call this Ka. Now the other one I have is when my NH3 group is acting more like a base, or my nitrogen-hydrogen group is acting more like a base. So if I wanted to write the base equilibrium dissociation constant, that's going to be NH4 plus OH minus over NH3. Okay, so according to what we just said, if we take Ka and multiply it by Kb, that should equal Kw. So let's see if that works. So I have NH3, H3O plus over NH4 plus times NH4 plus times OH minus over NH3. Okay, well NH3 is up here, NH3 is down here, those cancel. NH4 is below here, but NH4 is up here, those cancel. So ultimately the only thing that I have left is H3O plus hydronium concentration times hydroxide concentration, and guess what? We know that's equal to Kw, which is 1.0 times 10 to the negative 14th. So we can prove that the acid dissociation constant and the base dissociation constant, if we multiply them together for a similar type of acid-base situation, it should give us the Kw. Okay, we're going to stop here, and we'll do some more practice with these in class tomorrow. Bye, guys. Have a great night.